So now we talk about the quantum mechanics. So it's mentioned that light as a probability wave 是一个几率波啊，几率波。So the probability that a photon will detect in any small volume center on a given point in a light wave is proportional to the square of the amplitude of the wave electric field vector at that point. So this quick review for the chapter 35. Actually, we did not cover that chapter, but I suppose you should have learned it in high school. 就是那个双狭缝干涉。So actually, if we have an incident plane wave from this side, from the left side, and then there are two double slits here and here. So these two slits is very close to each other, and then these two, so these two will act as the source. They act as the source of this wave, and then it will start to propagate, and then they will somehow they will superimpose at this point, this point, this point, this point, this point, this point, this point. They will be superimposed, and for this point, this point, this point, this point, this point, they are cancelled with each other. So you will see the pattern will be like light, dark, light, dark, and so on. And actually, this is a Fourier transform. Actually, a Fourier transform of the light wave. So you see the light should have the property of the wave, and in the previous one, the light should have the property of the particle. Should have the property of particle, which means both of them are guaranteed by experiment. And so we start to feel that the light should be have some sort of a duality, 是那个破力二象性啊，破力二象性。Okay, so there are lots of texts. So consider double slit experiment again. Since the inference pattern eventually built up on the screen, we can speculate that each photon travels from source to screen as a wave that fill up the space between the source and screen, and then vanish in a photon absorption and some part of on the screen with a transfer energy and momentum to the screen at that point. 有点题外话可以提一下，就是这个就有点像那个你们用的 router 不是有几根天线吗？那几根天线的话，就有点像这个，它可以做一些叫做 beamforming 的动作，然后它两个波就是同时打出来，那在某些方向它就会叠加，某些方向它就会消掉，那就会起到一个指向性的信号阐述的效果，就有可能就是我放个 router 在这里，我指向你，我本来如果你只放一个天线的话，它就是往所有的方向传输出去的，或者在也许在某一小个角度可能会弱一些，但是比如说我们的手机它会设计成它往外面，电磁波会传输的比较好，它往里面会传输比较差，所以你带着手机的时候，你最好就是背面朝外，不然你所有电磁波是朝着你自己发射，你全部都打进你身体里面，所以它是设计成就是那个机壳上面就是有很多圈的天线在上面， 以前的手机你可以拆下来啊，如果你有试过拆下来的话，你就会觉得哦，为什么你的讯号就突然会弱很多？就是因为那个天线都在那个机壳上，你拆下来之后，你天线就拆掉了，就拆掉了，变成它的 impedance 都不匹配啦，或者是怎么样？那你如果继续学那个电磁学啊，或者是什么天线那个课，就会学到那些什么 impedance matching 那些东西，那都是跟那个 Maxwell equation 很有关系。所以你这个学期学得不好，你之后还要再痛苦2个学期啊，或者是痛苦2课。Okay, so let's move on. So here it's talk about the light as a probability wave. So we may consider if there are many photons, they may be somehow like they influence with each other. So it's somehow like maybe one photon going to this way, maybe a photon going to that way. But actually, this is not the case. For this experiment, it is published in 1992, actually like less than 30 years ago, so it's quite new. And so published on the Journal of Optical Society of America. So for this experiment, they try to generate a single photon. And for this photon, it can go in 2 paths. Path 1 is somehow like this, and then this is a mirror, so that it will go back. And for the other path, it is this way. And then this is another mirror, and then it will go back. And then this B is somehow like a, I'm not sure how to call it. Yeah, actually it can make some wave to go in 2 paths. It's somehow like a, it should be somehow like a splitter. 就是那个分光镜啊，就是 actually the wave for this one, when it goes this way, some of the wave will be reflected, and some part of it will go through. If you have many photons, and for M2, for path 2, if it goes this way, still some of the wave will go this way, and some of it go this way. Somehow like that. So the scientists may consider, there are many photons. So part of the photons go on path 1, part of it will go on path 2. So they will influence with each other. But actually not. This experiment tells you that actually even it emits a single molecule. A single molecule is emitted. Actually, the single molecule go on both paths, and the molecule itself interfering with itself. And then we can observe it here. So when the molecule in the source emits a single photon, does the photon never travel along path 1 or path 2, or can it be moved in both directions at once? Actually, this experiment showed the photon move in both directions at once. To answer, we assume that when a molecule emits a photons, a probability of wave radiate in all directions from it, and chosen to be near opposite to each other. So we can interpret all 3 versions of the double slit experiment if you assume that the light is generated in the source as a photon, So within this experiment, we observe the photon. So this is a particle, and then the light is absorbed in the detector as photon. So here is photon. But in between, it's somehow like a wave. It's somehow like a wave. And then because it has the interference, so the wave go in the path 1 and path 2 and inference with itself here. So we can observe the inference pattern. So within the same experiment, we observe both particle and wave properties for the photon. So further, de Broglie, this guy proposed that, so for wave, it has the duality. So he also suggests that for particle, it also has the property of wave. So this means that it is called the matter wave, 物质波，就是本来就是那个我们知道光有那个波粒二象性，就是有波动的性质，有粒子的性质。那这个实验呢，我们就同时观察到，就是同时具有粒子跟波动的特性啊。前面的实验就是这个实验有波动的特性，那个实验有粒子的特性，这个实验就同时具有两个特性。然后后来就有一个实验，就是他用电子，so we have incident beam, X-ray or electron, so electron, and then it should have somehow like the inference pattern. So for B it is X-ray, so it's a light wave. So for C it is electron beam. So they have a similar pattern. Although they are not exactly the same, but you can see this ring. You can see this ring, and then you can see this ring. Maybe the inside maybe a bit different. Maybe the resolution are not different. And actually, this is wave. This is X-ray. This is electron. They can't be exactly the same. Maybe you tune the light, tune the contrast. Maybe they will look more alike. But at this, you can see this ring. They are somehow like the inference pattern. So actually, not only the light wave should have can be inferent with itself, or also electron can also have the wave property. So for de Broglie, in his PhD thesis, he proposed the concept of matter wave. So previously we know that lambda equals h over p for the photon. Maybe somehow like here, p equals h over lambda for the photon. But here, he proposed that it is also suited for the matter, for the particles. So he calls the matter waves. So here's a sample problem. So what is the de Broglie wavelength of an electron with a kinetic energy of 120 eV? So actually we will use the equation like k equals p squared over 2m. Although usually we'll use k equals 1/2 mv squared. But for quantum mechanics, k equals p squared over 2m will be used more frequently, because actually you know that P equals mv. So P square equals m square v square. And actually these two equations is actually the same. So we can have a P equals 2 mk, take the square root, which is 2 times for electron. The mass is 9.11 times 10 to minus 31. And then the kinetic energy is 120 eV. So 120 times 1.6 times 10 to minus 19. So it is 5.91 times 10 to minus 24 kg/m per s. So the wavelength of the matter wave is h over p. So it is 6.63 times 10 to minus 34 over 5.91 times 10 to minus 24. So it is somehow like 112 picometer. 112 picometer, which is like 0.1 nanometer. 0.1 nanometer. So which is very, very small. Very, very small. So and the next one we talk about the Schrödinger's equation. Actually, this is actually not the Schrödinger's equation, but the wave function, 波函数. So if a wave function phi x y z t, so we have the coordinate x y z and the time can be used to describe the matter wave. Then its space and time variable can be grouped separately and can be written in the form like this. So actually, it's somehow like the separable of variables, which I have mentioned in the supplementary note of chapter 32 or 33, I'm not sure, 33 maybe, when I derive the wave equation. Which means that as long as maybe the potential energy of the system doesn't change with time, then we can just separate the time component here, and then this part only related to the coordinate of the particle. This part only relate to the coordinate of the particle. And this part is somehow like the exponential I omega t, which we should be quite familiar with it. It's somehow like the Fourier transform term, right? Because when you do the Fourier transform, it's somehow like xt exponential minus j omega t dt from minus infinity to infinity, right? And then this one is like that. And when we learn the plane wave, we should have similar stuff, exponential to I kx minus omega t. So we have, so this one is maybe like this term, or this term, this one maybe, yeah, this term here. So in the supplementary note of this chapter, we'll see why, or at least one explanation why it looks like this. Actually, the wave function is very strange. Wave function have no physical interpretation itself. 就是波函数并没有它的物理意义的。波函数是一个 complex 的一个 function， 是一个 complex function。 它有物理意义的是在于这个 complex function 取完绝对值的平方，它是一个 probability density function， 它是一个几率密度函数啊。So the interpretation, yeah, there are no physical interpretation for the wave function, but it is very useful. But it is very useful. It is the solution of the Schrödinger's equation. So you may ask, oh, why we need this wave function without physical interpretation? So one interpretation to it is we can calculate the absolute value of the wave function and then take the square. It will be the probability density function. So the probability per unit time of detecting a particle in small volume center on a given point in a magnetic wave is proportional to the value of phi square, absolute of phi square at that point. 所以我们计算完那个 wave function 之后，那我们取个绝对值平方，我们就会知道那个粒子啊，比如说某个量子在那个空间呢，它出现的几率是怎么样？我举个例子，就是比如说有一个波函数是描述我的行为的话，那可能这个函数啊，它就是说我可能有很大的几率我会出现在我的家里，然后有一些状态我可能会出现在我的办公室，然后有一些状态我会出现在这个教室或者隔壁这个教室，因为这个学期要上课。那我在这个地方的话，我的位置是不是固定呢？也不是固定，因为我有时候会往前往后，有时候会走过去，或者是怎么样。所以我在这个状态之下，可能几率会比较大了。那在这个附近的范围，可能出现的几率都会比较大。那有可能在外面的路走的时候，可能会有一个相对比较小的，又或者是说在洗手间，也许也有一些几率的。那这个 wave function 它取完这个几率密度函数之后，就类似像这种形式。Okay. So actually, this is the Schrödinger equation. This is actually a PDE, or at least this is the time-independent Schrödinger equation, which is already the simplified version of the Schrödinger equation. And in the supplementary note, I will let you know why it will look like that. It is not a proof. Richard Feynman has said that there are no proof. Schrödinger just come up with this equation and find it is useful. And all the experiment satisfy this simple equation. So that's why we need to learn it. Although we cannot really prove it. But actually, if we have something like the assumption about the plane wave 平面波的那个假设，再加上一些古典力学的那种动量加位能等于一个总能量somehow like kinetic energy plus the potential energy would be the total energy. If we have these two assumptions, then we can come up with this one. In the supplementary, I will show it to you. But actually, for this moment, we just accept this one. It's correct. Actually, it should be correct. So in this textbook, it is written like the second derivative of the wave function, the first term, and then here it is 8 pi square m over h square. So we know that a pi is 3.14 dot dot dot, and then m is the mass of the particle, h is the Planck constant, And then this E is the energy, is the energy of the quantum of the particle. And then UX is the potential, So we learned the electric potential in chapter 24. So this is another potential energy. Maybe you already learned this in mechanics. So you have somehow like mgh is the potential energy or whatever. So Ux is the potential energy, and this is the phi. So this is a second order differential equation. So for free particle, and actually in this textbook it doesn't use h bar, but previously I let you know h bar is actually h over 2 prime. So if we use h bar to write this equation, it will look a little bit simpler, because we don't have pi square here. So the pi square and the 2 square will be absorbed by here. So we only have 2 pi over h bar square. Look a bit tinier. Okay. So for free particle, Ux is 0， 就是没有位能在外面，它就很自由。那就是说，就好像说你要困住一个人啊，你就把他锁在一个房间里面。那这个墙壁啊，就好像一个位能的墙壁。那比如说我前面有一幅墙，那可能上面是通的。那我如果手上拿着一颗球的话，如果考虑古典物理的话，那我就要把它这个球啊，给它足够的动能，它才能够越过那个墙壁到墙的后面。在古典物理之下，如果我给的动能啊不够那个位能高啊，那个位能可能就是那个 mgh。如果我给的动能不够高的话，它就不可能越过它的。但是量子力学就不一样，量子力学的话，如果那个墙啊不是很厚的话，那我如果动能不够高的话，也许我那个粒子啊可以穿过那个墙跑到我外面去。那如果学那些量子计算的话，他们有一些叫做 quantum dot， 就是他们需要控制一些电子怎么样去，他们是要一个一个电子控制在某个地方去帮他们做运算。所以他们有一些叫做 quantum dot 的东西，他们就是用一些位能墙把一个电子困在某个地方，那可能它就要加某个电压，那个电压就是很高，那个电子就没有办法穿出去，但是它其实还是有几率会穿出去，就看你给的那个能量多大而已。Okay, so here,所以现在就是讲说自由粒子就是没有那个位能，那它就很自由，就是好像在Chapter 33的时候，我们说当我们没有电流、没有电荷的时候，那个 EM wave 啊，就是很自由的传播，那它就会讲得上一个 plane wave 如果我们有一些电流或者是怎么样，它就不会像一个 plane wave。因为比如说我们要产生一个电磁波的时候，我们如果用一根天线，那我们天线的话，我们就给一些电流，一些固定 pattern 的电流，它就会产生我们想要的电磁波出来，就是那可能那个天线就要经过特别的设计像一个什么线圈那样的，它可能就会产生出一些电磁波出来。So here, moving particle on which the no net force acting on it, the particle total energy in this case is all kinetic, and the equation becomes So here we make u equals 0 and e is e equals to k, and then equals to 1/2 mv squared. So we substitute it here. So we have m squared here, v squared, which means m squared v squared is p squared. So we have p squared. And then we have 8 and 4, so they can reduce. So we have 4, so it is 2 squared. And then we have pi squared, h squared. So we have something like this. And according to this one, the Blocky wavelength, lambda is h over p. Lambda is h over p. So p over h is 1 over lambda. 1 over lambda. So this one is actually 2 pi over lambda. And this is k. And this is k. So it will be reduced to a second order constant coefficient ODE. Constant coefficient ODE. So for this one, we can simply write the solution to be exponential to ikx plus a b exponential to minus ikx. So you should be familiar with how to solve this kind of second order ODE. So far we know that E equals HF, or we can write it as H bar omega. Or the other one, P equals H over lambda. Or we can write it as H over 2 prime and then 2 prime over lambda, which is H bar K. So these two equations is very useful. These two equations is very useful. So in previous slide, I already write it. The solution to 38.22 is this one. And actually, we allow the wave function to be a complex function, so that we don't really write a cosine kx plus b sine kx. We leave it to be a complex function. And actually, also a, b are also complex coefficient. Complex coefficient. And in this way, we keep in mind that the plane wave is look like this. Yeah, we have this plane wave. So consider free particle travel only in positive direction. Only in positive direction. We can just ignore the second term. Just discard the second term. So we let the arbitrary constant b to be 0. And at the same time, let us relabel the constant a as phi 0, just because it's just a constant arbitrary coefficient. So no matter it's called a, and phi 0 is fine. So here we have phi x equals to phi 0 times k. Phi 0 times exponential to ikx. So previously I tell you that this one doesn't have a physical interpretation, but for this one, the the absolute square of the wave function has the physical interpretation as the probability density function. So we can actually take the absolute value of this one. So phi 0 take the absolute value and then square. It is phi 0 square. And then for this one, if we take the absolute value and then square, which is nothing but 1, this is 1, right? Because exponential ikx is nothing but cosine kx plus I sine kx. So if you take the absolute value, and then square, it is nothing but cosine kx square plus sine kx square. So it is nothing but 1. So actually for this plane wave, the probability density function is a constant. Which means that for free particle, you don't really know where the particle should be at, because it is free. 它很自由的时候，你就不知道它在哪里。就是好像，现在要上课，那你在学校的几率就会比较高，但是你在放假的时候，找到你的几率就会很低。你就不知道跑到哪个地方，或者根本就离开澳门也不一定。但现在可能离开澳门不是一个很好的选择。Okay, so here we talk about the Heisenberg uncertainty principle, 海森堡测不准原理。Okay, so in the textbook it tells you that delta x delta px is larger or equal to a h bar. But actually, for more rigorous result, it should be somehow like the sigma x times the sigma p is larger than or equal to half of h bar, which is a very, very small value. So it tells you that Heisenberg uncertainty principle says that measure value cannot be assigned to the position and the momentum of a particle simultaneously with unlimited precision. 所以 and then here delta x delta px represent the intrinsic uncertainty in the measurement of the x component, with parallel meaning that for the y and z. Even with a best measurement instrument, each product of a position of uncertainty and a momentum uncertainty will be greater than h bar nevertheless. 那我有听过两种解释，一个就是说，你对于比如说一个粒子，你要知道它的位置跟它的动能动量位置跟动量 ，x 是位置，p 是动量。那动量的意思就是它的速度嘛，就是你要知道它的位置跟速度，同时都知道精确的话是不可能。你一个越准，另外一个就会越不准。那它们的乘积乘起来就会大于一个数，那这个数就是 h bar over 2。那有另外一种解释的方法是说，你观测一个粒子它的两个物理量，比如说在这里是位置跟速度。有另外一个版本的海森堡测不准原理是说是频率跟时间，就是好像你做那个傅里叶变换，就是频率跟时间。那这里也可以做傅里叶变换，你就是从 x domain 变成 p domain。那就是说，你先测一个，再测另外一个。你比如说，你先测 A 物理量，再测 B 物理量，跟你先测 B 物理量，再测 A 物理量是不一样的，这个就比较复杂的，就可能需要一些量子力学的一些知识一些更进阶的知识才会 理解这句话到底是说什么回事。那我们实际啊，我们在宏观世界去看的时候啊，我们并不是看到那种物理量的某一个值，我们是看到那个值的 expectation value， 它的期望值哦，就是比如说我们看到，比如说一些粒子，那些粒子，比如说我们有个电流，我们看电子流动的速度，我们不是看电子流动的速度，我们看一个宏观的话，我们就看到一个电流。那电流的话其实就是一个电子平均的速度这样的一种概念。因为你有一些电子可能它就跑得比较顺畅，有一些可能它撞到某些东西，它就要改变方向或者怎么样，那可能它就跌跌撞撞的往前走。那我们只能看到一个宏观的一个观测结果。所以啊，对于free particle，so for free particle we assume yeah, we know that let me see, phi x is actually exponential to I k 0x. And then we also know that P equals h bar k0. Maybe you can write k, but here I make it k0. So if delta p is h bar delta k is zero, which means that if this p is very, very small, then delta x would be tends to infinity. So it's somehow like maybe we know this is related to the wavelength, and the wavelength relate to the frequency. So maybe we can measure the particle wavelength, maybe like this. Maybe very it is only a single frequency or a single wavelength particle. So in signal and system, you know that if it is infinitely narrow, so this is a delta function, delta, and this is k, so this is delta k minus k0. So you take the Fourier transform, what is it? 有搞錯咁簡單嘅都唔記得。你個 table 我哋雖然冇人記。So when you take the Fourier transform of the delta function, it should be something like this. So actually, if it is delta k, your Fourier transform should be 1. And if it is delayed by k0, then delta k minus k0, it should be shifted by exponential to I k0 x. Should be something like that. So this one should be the x. This is the phi k. In the k domain, if you know this to be very accurate, this is very narrow, then in the x domain, it should be very flat. It is a uniform distribution. So when you take the absolute value and square, it should be 1. Right? or actually 2 pi. Maybe for different textbook, the definition of the maybe for the one you learn in signal and system, maybe 2 pi, not actually 1, but actually when you learn Fourier transform in different textbooks, they have different definition. Some text in signal and system, what you learn is maybe xt exponential minus j omega t dt, and then this one. And some textbook may be something like this, exponential to minus j 2 pi ft dt. And then this is in the f domain. This is xj omega. Some textbook maybe look like that. And some textbook maybe look like xt exponential to I alpha t. maybe different. So so it doesn't really matter. You just adopt it. It's fine. But this one is tell you that if you know the momentum to be very accurate, then the position would be very inaccurate. And this is due to the Fourier transform. Actually, they are the Fourier transform pair, the momentum and the position and the displacement. And another example is somehow like if it is a normal distribution, a Gaussian distribution. So if phi k is somehow like 2 pi sigma k exponential to minus k minus k0 to sigma k square. If it is somehow like that, what is the Fourier transform of it? Actually, it is still a Gaussian distribution, but with a different standard deviation or the variance. Maybe I don't have enough time to show it today. Maybe I continue next week. So let's stop here.